Okay, so welcome to Scaling LightGBM Training with Dask. My name is James Lamb. I'm an engineer here at Saturn Cloud, and I'm also one of the maintainers of LightGBM. Okay, so first I just want to give you a little introduction to Saturn, just in case some of you here are maybe not too familiar with us. So Saturn is a managed solution for scaling your Python workloads. So we really like Dask. We talk a lot about Dask. But we are not only about Dask. We have put together this managed solution where we combine these open source tools that you know and love, like Project Jupyter, Prefect, Dask, Kubernetes, and give you kind of an ability to take your code that you've already written in Python and make it faster or run it on more machines, larger data sets, and do cool stuff. And I'll show you that more in the demo as we go. All right, so first let's talk about why Dask. So this talk is about LightGBM in Dask. And I think that before we get to how LightGBM works and why there's a LightGBM Dask extension, we need to talk about why people use Dask at all, like what it's good for. So data scientists love to work in Python. Maybe you have worked in some of these libraries before. Scikit-learn, Pandas, this array library whose pronunciation is controversial. I like to call it NumPy, Apache Arrow. These projects are great. They have they've benefited from a ton of effort by maintainers, really good community, really good documentation. However, those libraries were designed to work on a single machine. So when you work with Scikit-learn, when you work with NumPy, they kind of work best on a single machine. Think of like your laptop or maybe a virtual machine that you get from a cloud provider or something like that. And so what that means is if your problem gets larger than can fit on one machine, those libraries, you might find it difficult to still work with them. And I want to stop here and be sure that I explain what I mean by your problem get larger. So when we talk about big data, big ideas, this doesn't have to mean your data set got larger, that you have, on the order of terabytes of data. Your problem can get larger if, for example, you're doing machine learning training and you want to run more experiments. You want to search more possible combinations of estimators, of features, of hyperparameters. So there are a lot of different dimensions along which your project can get bigger. And this is really not what these libraries that I just talked about were designed for. I also want to stress, sometimes when I've had conversations about this with people and I've heard the pushback like, well, like maybe this is cool, Dask, Spark, Ray, seems interesting to me, but my problems are pretty small. I don't really need to worry about that. I would just ask that you consider how small the problems you're working on are and how close you are to the limits of these libraries. So, for example, there is a great blog post that was turned into a conference talk by Wes McKinney, the creator of Pandas, called 10 Things I Hate About Pandas. And in that talk, in that blog post, he said that his rule of thumb is that for any given data set size, if you want to work with that data set in Pandas, you need to have 5 to 10 times as much RAM as the size of that data set on disk. So, even for a data set that's maybe like single digit gigs, maybe 10 gigs, you could already find yourself at the limits of kind of your local development environment, the environment that you're used to working in. So you can run into the limitations of kind of single machine computing on your laptop or on like the free tier of a cloud service pretty quickly. Okay, so we're going to talk a lot about machine learning work in this talk specifically. And so when your machine learning work demands that you use more physical resources than you have, you kind of have three options. Your options are basically downsample your data, get a bigger machine, or use more machines. And so in the downsample your data, what you might do is take your raw data that's kind of much larger and store it somewhere else in a system that can handle queries over that data. So you might store that in files in an object store or a file system and use one of the query over files types of tools like Presto or Drill or Athena, something like that. You might store that data in a data warehouse. You might use something like Redshift, BigQuery, Snowflake, something that will let you kind of write SQL over your data and that will kind of allow you to push most of the work of getting the data set down to a size that fits on your machine out into a dedicated query layer that can handle it. Or you might just use, a traditional database server, something like Postgres or something like that. Another option that you have is just to get a bigger machine. You can go to any public cloud provider and get a bigger VM. That can cost money. And as you get to the larger and larger sizes of those VMs, you can face some capacity constraints. So despite what some cloud providers marketing might tell you, the cloud is not infinitely elastic. And as you get into the larger instance sizes, there is less availability of those. So you can run into some issues. And when I talk about the expense of getting a larger machine, that doesn't just mean the obvious, more RAM and CPU is more expensive. Of course it's more expensive. When you're dealing with one large machine, you're paying for the entire capacity of that machine as you use it. Whereas if you can put together the same cumulative resources from many smaller machines, you might have some opportunity for your workflows to scale individual pieces up and down during kind of the peak and trough busyness parts of your workflow. So all kinds of interesting stuff there. And then finally, you might want to use more machines to solve your problem. So there are some very specific frameworks for doing this. LightGBM, XGBoost, TensorFlow. These projects have written their own distributed computing things that are highly specific to their use cases. There are also more general tools like Dask, like Ray, like Apache Spark, Kubeflow, projects like this. So these are kind of your options when your problem gets larger than your laptop. Let's talk a little bit more about those ML frameworks. So if you go look in the code bases of XGBoost and LightGBM, for example, you are not just going to see things that you would consider machine learning-y things. You're going to see people implementing all of the main MPI operations. You're going to see low-level code that is managing sockets and probing for open ports and doing all kinds of weird stuff. And that's because each of these frameworks on the screen, they've created their own distributed training, basically libraries or maybe they've bundled those into their own libraries. And these are great for the work that these frameworks do, but they're not general purpose enough to allow you to do whatever you want. So for example, if you use distributed LightGBM, once your data is kind of ready to go, you've created all your features, you've chunked up all your data into different pieces on different machines, that should work pretty well for you. And it should go well, it should train quickly, and it should allow you to solve a problem that's bigger than your laptop. However, LightGBM is not going to give you a way to do feature engineering in a distributed fashion. It's not going to give you a way to do data loading in a distributed fashion so that you don't have to say load chunks of the data on your machine and then push them out over the network to those machines. So these frameworks are great if your data set is kind of just ready to rock. But if you need to do other prep, pre or post processing, then those distributed frameworks might not quite be enough. And so that's where you need a more general purpose solution. And the one that has been really popular for a couple years, the one that many companies use is Apache Spark. Dask has very similar aims to Apache Spark. There's a decent amount of overlap in the use cases that they cover. And I expect that most people who are here today have some familiarity with Spark, or at least, have heard about it in conference talks or something like that. So next, I want to just go over a little bit of the similarities and differences between Spark and Dask. Now that we've kind of established what the need is for these more general purpose frameworks. So I want to start by telling you how these two things are really similar. So both Spark and Dask allow you to do distributed machine learning training. In Spark, you can use MLlib, you can use Spark ML. There are some frameworks that create Spark extensions. So for example, if you are working in Scala or other JVM languages, you can use XGBoost for JSpark, which is a really long name, but it's a really great project. And you can do distributed training. Well, you can do the same thing with Dask. You can use the Dask ML project that's kind of from the core Dask ecosystem. There are some projects called Dask XGBoost and Dask LightGBM, which have been around for a little while. And I'll talk a little bit later about kind of the things that are replacing those projects very soon. You can use TS-Fresh for time series work. Both of these can allow you to do distributed machine learning training, which is cool. By the way, I want to be sure that I explain this. I realize I didn't before. When you hear me talk about distributed machine learning training, that is not necessarily synonymous with parallel. So sometimes in the guides for these frameworks, you'll hear people talk about parallel training. The two concepts are related but not identical. When you hear me say the word distributed, I don't just mean that you're doing multiple things at once, that you're multiprocessing. I mean using multiple machines, which each have processes running on them that contribute to the overall training. Okay, wanted to be sure I clarified that. Both of these libraries also support distributed data structures. So in Spark, you have the RDD, the data frame, a distributed matrix, and Dask has these as well. Dask has a collection called the Dask Array, which looks and feels very similar to NumPy, for those of you who like to say it that way. There's a Dask data frame that's kind of similar to Pandas, but distributed. So both of these will allow you to solve machine learning problems without ever having to hold all of the training data on your local machine, or without having to use your local machine's CPUs or GPUs to proceed and accomplish that training. Okay, but there are also some important differences, and let me take a sip of water while you read this. Okay, so one of the biggest selling points for Dask is that it is Python first, and it's Python all the way down. I mean, all Python code eventually ends up in like C or some Fortran or something, but from a user perspective, it's all Python all the way down. This is really different from Spark. So you can work, of course, on Spark in Python. PySpark is a large and popular project. It's been a part of Spark for a number of years. People use it successfully every day to create business value. But in PySpark, you are still eventually, PySpark is kind of a wrapper on top of the core elements of Spark, which are written in Scala and Java. And so what that means is maybe you've had this experience where you execute something in PySpark, you're ready, you think like your job's definitely going to succeed, something goes wrong, and then you're staring at like 100-line Scala stack trace, and you have no idea what to do because you know Python and you don't know Scala and you don't know Java. That experience is not going to happen in Dask because Dask is Python all the way down. And being Python all the way down also means that the behavior of writing highly custom stuff in Python is a little bit more predictable and it's easier to debug. So, it's different than writing like a Python UDF, a user-defined function in Spark, where the handoff is a little bit unclear and there's a little like more guardrails. In Dask, you're basically writing functions that are getting serialized with pickle and sent around, and like it's all beautiful and it's great. Now there's things that go wrong, but there's less friction I found writing Python code in Dask than working with PySpark. The next big feature of Dask that I think is a benefit compared to PySpark is that the Dask ecosystem has put a lot of energy into API parity with those libraries that I showed a couple slides ago. So the Dask data frame, it looks like Pandas. Your code looks almost identical to Pandas. DaskML, when you use DaskML's grid search CV or something, it looks and feels just like scikit-learn. It's not 100%, it's not perfect, but they have put a lot of effort into that in the Dask ecosystem. And in fact, some of the contributors and maintainers in the Dask ecosystem are also contributors and maintainers from those libraries, from Pandas and from scikit-learn. So that's a really cool feature because you don't have to feel like you're writing Dask code. You don't have to feel like migrating from stuff that runs on your laptop to something that runs on a distributed cluster involves a large rewrite and like a re-architecting, which is fun. Dask next will give you finer grain control over the work that you do. So I'll talk more about the Dask task graph in a little bit, but effectively what this means is, think about when you first learned Spark. For those of you who've used it, you learned about these functional programming primitives like filter, group by key, reduce by key, these things. Dask doesn't put those guardrails on you. And it will allow you to basically create any computational graph that you want without having to kind of twist yourself into knots to make it happen, which is cool. And then finally, Dask has support for multi-dimensional arrays, which at least as of when I wrote this slide, Spark did not. So for those of you who are working with, data, like problems that require multi-dimensional arrays, Dask is going to be your friend. Now, to be fair to Spark, there are things that Spark has that are benefits over Dask and reasons that you might choose it. The biggest one, I think, is a SQL engine. So Spark SQL, it kind of just works. You have a bunch of tabular data in files or a database or something. You write Spark SQL against that data, and you get a data frame with the result. And you can rely on Spark to optimize some things, to like execute that fairly quickly, to try to minimize the memory consumption. Spark Dask doesn't really have that. There are a couple of incubating projects in the Dask ecosystem. There's Dask SQL, Fugue, and Blazing SQL, to name a few. But because Dask is more flexible in the way that it defines a task graph, because it doesn't have those guardrails that I talked about in Spark, it's a lot harder for Dask to provide a really like performant and good experience with SQL. So if most of your work is writing jobs that are just like executing SQL over tons of data, Spark actually might be a better choice for you. Very closely related is that Spark has more high-level optimizations of your code than Dask can offer. So because Spark puts those guardrails in place and there's like a very specific set of things that you can do, it means that Spark has the ability to look ahead before it computes all of the stuff you want it to do and say, oh, you know what, actually, like there's this filter step all the way down at step 8 of James's pipeline. Well, if we're just going to filter all these other results, we might as well move that up to the beginning and filter that data right from the beginning, things like that. There is some of that in Dask. I don't want to undersell it. You know, there is optimization happening on the graph in Dask, but it might not be as powerful as Spark because there are less guardrails, because that optimization has to account for more custom stuff. If you're working with a lot of graph data, you might find that that's easier to do in Spark. If you're solving graph problems, you know, looking at like, social graphs of people connecting on networks or something like that, you might find that working with GraphX is a better experience than the equivalents in the Dask world. And then finally, the biggest one, if you don't want to work in Python, Dask is probably not for you. So Spark will support writing your logic in Java, in Scala, in R, in Python. Dask is really intended for Python. It's Python all the way down. They have kind of made that commitment. So if you are like, I really like writing R, I want to use Dask, it might not be the best choice for you. And you might prefer Spark or learning Python to write Dask stuff. Okay, that's all I want to talk about. This could be like a whole other talk. And honestly, I'm not the most qualified person to go too much deeper into this. So let's move on from the Dask versus Spark stuff. But hopefully that gave you a general idea of why the LightGBM project even cared about Dask, and why we care about Dask here at Saturn. All right, we've learned about why. Let's talk about what Dask actually is and how it works. And I'm going to take another sip of water while you read this slide. Okay, cool. So I'm going to talk for the rest of this talk about using Dask for a multi-machine task, for a distributed task. I want to say one time here that Dask works great on a single machine. Dask as a process as a framework for just doing multi-processing on a single machine is awesome. The experience is frictionless. I really have had good experiences using it for that. So I don't want you to walk away from this talk thinking, okay, I don't need to use Dask because I don't have multi-machine problems. Dask is great on a single machine. This talk is not about that though. So everything from this point forward will be about distributed problems. Okay. So Dask is not a library. Dask is an ecosystem of many different libraries. And so I'm going to talk about a couple of them. And when you see this kind of bright purple notation, that means that I'm talking about one of these sub-projects in Dask. Okay, so let's talk about distributed. So when you work in Dask, there are these three key concepts: the client, the scheduler, and the worker. So the client you can think of as like code that you write in a notebook or something like that. The client is the thing that connects to a Dask cluster. The client is the thing that knows how to tell Dask to run your stuff. So you write your code, you tell the client, hey, like go tell Dask to do this, and then it tells Dask to do that. The scheduler is the thing that knows how to take those decrees, those questions from the client, and then turn around and actually get them done and report back to the client whether or not they were successful, how long they took, how much memory and CPU they used, et cetera, et cetera, et cetera. So that's this kind of second layer of the scheduler. And then the scheduler accomplishes its work through something called workers. And so the workers, I'll talk about in a second, the workers are processes. They have some physical resources that they're allowed to use. And the workers just know how to take instructions from the scheduler, do the thing the scheduler asked, and then tell the scheduler how it went. And they can tell the scheduler things like, I did this, I tried this and it failed. I am still doing this, and a couple of other things. I think that this image from the Dask docs, well, technically I took this image from one of the Dask maintainers talking in a thread on a GitHub issue, but it's basically from the Dask docs. It's from one of the Dask contributors. I think that this image really shows an important point, and that's that in the Dask ecosystem, you can plug in different choices at each of these levels of client, scheduler, and worker, but all of your other code, it just needs to talk to a Dask client. So when you change from running on your laptop to running on, Amazon EKS to running on a managed solution like Saturn, you don't really have to change very much of your code. You just change the code that creates the cluster and that connects to it via the client. Okay, so as I go here and talk about scheduler and worker, I'd like to explain another thing that was confusing to me when I started working with Dask. So the scheduler and the worker, these things don't have to imply physical machines. So I can have a 3-worker cluster on my laptop, on a Raspberry Pi, on whatever. The scheduler and the worker are processes. They're Python processes. And you can try this yourself. If you pip install Dask, pip install distributed, on your laptop, you can open up a couple of shells and you can run Dask scheduler, and then you can run dask-worker and pass it the scheduler address and create your own cluster just with those processes. And you can look at it in HTOP or whatever. So I want to be sure I make that point. When we talk about workers, worker is not one-to-one synonymous with machine. Okay, there are many options for running a distributed cluster. If you have an existing Spark cluster, you can use a project called Dask Yarn. So you can run a Dask cluster on, EMR from Amazon or something like that. If you are working in high performance computing and you already have an HPC cluster, you can use something like Dask Job Queue or Dask MPI to kind of already link into the way that your networking is set up there, the way that resource negotiation is set up there. Run a Dask cluster there. If you like using Kubernetes, maybe you have an on-prem cluster, maybe you're using something from a cloud provider, there's a Dask Helm chart. You can Helm install Dask, basically. There's another project called Dask Kubernetes, which will allow you to kind of set up Dask clusters in Kubernetes. So remember that picture that I showed with the client, the scheduler, and the workers? You can think of the client as running, say, like in a Jupyter instance in a pod in Kubernetes. Maybe you give the scheduler its own pod in Kubernetes, and maybe each worker becomes its own pod, or at least a process running in a pod in Kubernetes. And you can also deploy to public cloud providers. So there's this really great project called Dask Cloud Provider that kind of smushes together support for a bunch of different clouds. You can deploy to DigitalOcean, to different AWS services, to Google, to Azure, all kinds of things. But I think that what you'll find is that with these projects, once you get beyond kind of experimenting and kind of just trying out Dask, you'll find that some of the things that you need to do to actually do your day-to-day work in Dask are difficult with these open source projects. Like the way that you get credentials to all of your code so that if your code needs to hit a protected database or AWS resources or something, it can do it. The way that you distribute custom libraries to all of your Dask workers. A lot of the libraries that you see here, their ecosystem, whether it's built on containers or not, it's easiest to use when your code is in a package manager like PyPy. Well, that might not be true for your internal code. And so this is why a solution like Saturn can be valuable once you want to go a little bit further beyond some of these open source projects. But again, I want to be sure that you walk away knowing this. Whether you're working on Saturn or whether you're working on one of these open source projects, that choice of client and cluster you're going to see in the demo is very isolated to a specific part of your code. And you don't have to kind of drastically change the business logic of your code to pick and choose between these options. Okay, now that we've talked about schedulers, we've talked about clients, I kind of hand waved over this thing called work. I said, the Dask cluster does some work. Let's talk about what that work is. So all of your stuff is arranged into a task graph. So this graph on the right from the Dask docs, the square boxes here are inputs or outputs. The circles are tasks. These are basically Python functions. And And the arrows drawn between them show that there's an ordering in the graph. So when you do work in graph, when you do work in Dask, excuse me, there's an ordering, which means that there are things that have to run before others, or said another way, there's things that depend on others. Dask will look at that graph, and based on those dependencies, it will know which things can be done in parallel and which things have to wait for other things to be done. And so when Dask looks at your graph, before it actually, goes and runs your code, there's going to be 5 things that happen. And all of this is taken from the Dask documentation as well. So the first thing is construction. This is when you just tell Dask what to do. That's basically going to store a bunch of Python functions in a dictionary. That's kind of the simplest way to describe it. After that construction, Dask is going to do something called optimization. I talked about this a little bit in the Spark comparison. So Dask is going to look at your graph, and it's going to look for opportunities to reorder things without maybe hurting the functional correctness of your graph. So it'll look for maybe repeated steps that have no impact on the outcome, on the outputs, or something like that. Okay, your graph's constructed. Dask has done some optimization. Next, what's going to happen is serialization. So at this point, that graph is sitting there on the client. Think of that as like a notebook that you're running or something like that. But now that graph needs to get out to the scheduler. And so the graph will be written to bytes and sent over the wire to the scheduler, wherever that scheduler process is running. At that point, the scheduler then also tells the workers about the work that's going to be done. It sends the workers the task graph. All right, once everybody involved here, the client, the scheduler, and the workers, they all know kind of what you want to do. Then we get to a stage called scheduling. And so in scheduling, the scheduler kind of looks around at the workers that it has available. It knows something about the resources on those workers. It knows how much memory they have. It knows what other stuff they're doing right now. It knows whether they have specialized physical resources like GPUs or something like that. And the scheduler is going to be like, okay, I know that, in this case, task add needs to get done first based on this input Z. I'm going to tell this worker to run add, and I'm going to give this worker Z. Stuff like that. And so that's how scheduling goes. And scheduling is an ongoing process. So the last 2 steps here kind of repeat over and over again. Once work is scheduled onto a worker, the worker gets that request from the scheduler and is like, yep, okay, I'm on it. And then your code finally runs. This is what's called execution. So in this stage, your worker is doing the work and it's telling the scheduler all kinds of stuff. It's sending logs back to the scheduler. It's sending statuses, and it's telling the scheduler like, yep, I'm working on it. Or maybe, yep, I did it and I'm done. And you asked me to put this result somewhere, like here's how to reference this result. Scheduling and execution just continues until everything in the graph has been executed, or until some fatal error happens and execution is stopped early. And then the process is done and you do it all over again. Okay, so now we know that there's clients, schedulers, and workers. We know that they talk about what to do in graphs. Let's talk about how to build those graphs. And I'm going to take a sip of water while you look at this slide. All right, so the lowest level interface to building the graph is a project called Delayed. So this is a part of Dask. And what Delayed allows you to do is you basically write Python functions that are just normal Python functions. And then you wrap those functions in either this function dask.delayed, or you can put, there's a delayed decorator that you can put on your function definitions, whatever you want. But what you're telling Dask here is basically, here's a function. It's going to take in some inputs. Don't actually run the function yet. So what I'm doing in this little example from the Dask docs is I'm building up a graph like the one that you see on the right, also from the Dask docs. So what I'm doing here is I'm saying, okay, I'm going to run these functions inc and double. Inc is a function that just like adds 1, it stands for increment. Double doubles its input. I'm going to run these functions inc and double, take the results, add them together, and then I want to sum up the results of all of those individual adds. And so up until the final line of the code that you see here, actually all the way through the final line that you see here, nothing has actually happened. Dask has just set up this graph and it said like, okay, I know how to describe this work. I'm ready to do this. And then once you actually ask for this result, once you tell Dask to compute this, it will run this whole graph and give you back a result. All right, so that's the lowest level. The next level up that's important for machine learning work are these Dask collections. So the collections are data structures. If you're coming from Spark, think about the first time you learned about like a Spark DataFrame or an RDD. They're these data structures that you act on in your client code. It looks and feels like you have the whole thing right there in memory on your, on your laptop in your notebook. But in reality, the operations that you ask for are turning into Dask graphs that go and execute on different worker processes, which means possibly different machines. This image, I really think it describes it well. This is another one that was taken from just like an ongoing Dask issue on one of the Dask repos, but I really, really like it. This shows a NumPy array versus a Dask array. So on the left, you have a 6-element NumPy array. All of the things that are kind of light blue here, those are NumPy arrays. And so like in the top left corner, you can see we have 6 elements. And when you call the .sum method on the array, all 6 elements are summed and you get a result. And it just all happens like right in memory, right in your main process. Let's look at the equivalent Dask array. So in the equivalent Dask array, to your code, it looks like that 6-element array, but it's actually broken into 2 physically different pieces, a 4-element NumPy array and a 2-element NumPy array. These are the things that are labeled chunk 0 and chunk 1. And so when you ask for the .sum of the entire Dask array, it's going to turn that into a small Dask graph that says, okay, whatever worker has chunk 0, please sum that for me. Whatever worker has chunk 1, please sum that for me. And then it's going to get back those 2 sums, then sum them together, then give you that result. So that's kind of the way these Dask collections work. A Dask array is made up of possibly many smaller NumPy arrays. A Dask data frame is made up of possibly many smaller pandas data frames. And then a bag is sort of similar to an RDD in Spark. This is, it's an iterable object that has these kind of functional programming things like filter, reduce, things like that. And I actually don't recall if the underlying chunks there are lists or tuples. I actually don't remember. Okay, so cool. So we've got low-level graph. We've got these data structures. Well, once you have a distributed data structure, I can build a matrix that's split over multiple machines. Now we can start talking about doing machine learning. And so there are libraries for accomplishing machine learning tasks in Dask, which assume that your data, your training data, your validation data, the data you're predicting on are in these Dask collections like Dask DataFrame and Dask Array. And so the main one in the Dask kind of core ecosystem is called DaskML. DaskML tries to have an API that's similar to scikit-learn, and it comes with some built-in things that will let you, maybe do a grid search over distributed data. That'll also distribute the work of searching the different sets of hyperparameters. DaskML has some features for ensembling models in parallel and doing some other cool stuff. And then there are a couple of other extensions that are specific to specific frameworks. So the one that I work on a lot is LightGBM and a little bit on XGBoost. Both of these projects have native integrations where basically if you have data that's a Dask array or a Dask data frame, you can use xgboost.dask or lightgbm.dask, and those frameworks kind of wrap the underlying native XGBoost distributed learning or LightGBM distributed learning. And both of those XGBoost and LightGBM modules, to be sure that I give you a fair history here, originally were projects that incubated in the Dask ecosystem called Dask XGBoost and Dask LightGBM. So those projects were not written by the XGBoost and LightGBM maintainers. They were written just by people in the Dask community. But in the last couple of months, those projects have been kind of upstreamed into XGBoost and LightGBM. And I expect that you'll see, I expect that 6 months from now, we'll be talking about those packages as being archived. I hope that we'll be talking about them as being archived. Okay, let's talk more about that. So as I said before, if you have used Dask XGBoost or Dask LightGBM, or maybe you leave this talk thinking like, I'm going to go try out LightGBM on Dask, and you find some blog post that uses these libraries, I strongly recommend not using these libraries. They are not receiving active maintenance. There's not a lot of work going on them, and most of the work in XGBoost plus Dask is happening in the XGBoost project. Most of the work on LightGBM plus Dask is happening in the LightGBM project.
Hey, James, actually, there was one quick question that I think is relevant. Actually, back a couple more about how the sums happen in the arrays. There was a question of, does that final sum that's like comprising all of those individual sums also run like on a Dask worker, or is that something that happens like at the top level? How does that work out?
Okay, great question. I will just tell you I don't know the specifics of Dask arrays sum, but I'll tell you what I believe the answer to be just based on the general principle of how Dask works. So stay with me, but know that I'm not 100% sure that this is exactly accurate for .sum. When you finally need a materialized value, like you're not playing these games anymore with like delayed futures that you're waiting on, but you literally need the number. You literally need the sum. Ultimately, that thing has to be created in memory on the client. That's the place where you started your Dask work. So that's like your notebook or whatever. I don't know for sure whether that single sum is being computed out in a task on a Dask worker and only the number is sent over the wire to you, or whether that sum is happening at the client level. That's a decision that every Dask interface has to make of kind of how much to push out to the cluster versus how much to do on the client. So I hope that answers the question. I don't know the exact answer for the specific case of Dask arrays sum. And I don't know, maybe Aaron, if you know any more than I do.
I think that's the kind of the general idea that I would have too. It's, Dask will be intelligent enough to kind of split out like the big work out to the cluster, right? But that last final piece of like where that last sum is happening would have to kind of double check. But I would expect that anything that has a lot of like heavy lifting going on would still happen across the cluster because Dask wouldn't be pushing a lot of that work to the client.
Yeah, thank you for that. And I'll just add to that. This is one of the places where Dask's flexibility, this ability to do this delayed stuff is important, because if you find that maybe Dask has made a design choice in some Dask thing that you're using, where they've made a design choice to do some work on the client that you think is too expensive based on your data and problem, you have the ability to go in and do it yourself, to tack on stuff with Dask delay to push that work back out to the cluster if you'd like. You should expect that the libraries that are kind of core to Dask, they are written for general use, and they try to make design decisions that will be most useful for the most people. But that can result in situations where for your particular use case, it would be more efficient for something to be done on the cluster that is done on the client, or vice versa. So hopefully that helps. Okay, are there any other questions, Aaron, before I continue?
No, you're good.
Okay, thank you so much. Good question. Okay, now we've done all the Dask stuff. You've learned why Spark is cool. You've learned why Dask is cool. Hopefully you've learned why Saturn is cool. Let's talk about LightGBM. So LightGBM stands for Lightweight Gradient Boosting Machine. So for those of you who are not familiar with gradient boosting is an iterative process of supervised learning where basically you start with an initial assumption, kind of a base prediction. So think about like if you're doing a binary classification task, your base prediction with no other knowledge is just like the observed rate, the percentage of records that are 1 instead of 0, something like that. You start with a base prediction. Then you evaluate how well that prediction does on every record in your training data. You generate residuals. That's like the difference between the prediction and the actual. Then you train a model on those residuals. Then your new prediction is the base prediction plus the prediction from the first model. And then this process just continues and continues and continues. This is not specific to LightGBM. This is generically how gradient boosting works, is that you keep training these models on basically the errors of the model that is composed of all models up to that point. Now in LightGBM is a specific type of gradient boosting called a gradient boosted decision tree, where each of those intermediate models is a decision tree. And I'm going to talk a little bit about the specifics of how LightGBM is different than from others that you use. But the thing that I want you to keep in mind as we're talking about distributing LightGBM is that if you have a 100 tree LightGBM model, you cannot start training tree 2 before you've trained tree 1. It's not like random forest. And so that does impact which things can be parallelized, and as a result, which things can be distributed. Okay, so LightGBM is implemented in C++, and then it has wrapper packages in R, in Python, in Java. There are other projects that the LightGBM maintainers do not maintain, but that allow you to use LightGBM in Julia, Rust, C Sharp, like all kinds of stuff. Because LightGBM is a C++ library with a C interface, pretty much every major programming language has a way to hook into a C library. So there are lots of these extension packages. And I think sometimes people are surprised to learn that there's a LightGBM CLI. You can call like /LightGBM training data and do stuff with it. But what we're going to talk about today is the Python package, which as of the next LightGBM release will include first-class support for Dask. Okay, so one of the things that differentiates LightGBM from other gradient-boosted decision tree frameworks is that it grows trees leaf-wise. So let's look at this example from the LightGBM documentation. And as we go through this, think about what it would take to have multiple machines, which each have only a piece of the training data, contribute to this. So the tree all the way on the left shows the first decision that was made, kind of the first split that you made. So this is like, a split is a combination of a feature and a threshold. So this might be like all records where the value of age is less than 21, go to the left, greater than 21, go to the right, something like that. When I say that LightGBM grows trees leaf-wise, what that means is the second and third nodes that it grows, they don't have to keep the tree balanced. So if you skip ahead to the third tree here, you could see that we took that first split, then split those results further, then split those results even further. In other algorithms, they try to keep the tree balanced. And so after this second tree, you necessarily would have gotten a split on that right node. So you would have had, kind of balance all the way down. But LightGBM instead is made to go deeper. And so this has a couple of implications. One is that when you think about limiting the maximum depth of the tree, you have to think about it differently in LightGBM, because all else equal, LightGBM will produce a tree that's deeper and less balanced than other methods. So what that means is like, think about if we had max depth equals 2 here, right? That third tree never would have been created. That third split never would have been added, right? We might have added a split on that other node or something like that. So that does affect the process, but you can kind of think of it as like XGBoost is really, LightGBM is really trying to get you the most gain possible out of each incremental tree. And sometimes that means going deep, and sometimes it means going wide. Okay, I think I've belabored that point enough. One of the major reasons that LightGBM is fast is that it does this thing called feature histogram construction. And I think this picture from this blog post really describes this fairly well. So when you build a gradient boosted decision tree, or actually any decision tree, we forget about gradient boosting for a second. When you build any decision tree, you face this choice as you build the tree of which node to add to the tree next. And which node means which split point to choose. A split point is a combination of a feature and a threshold. And it says, we're going to move the data to the left or the right of this threshold. So let's look at this input data at the top, right? We have a 7-element array here. I'm very good at math. Thank you very much. A 7-element array here. And at seven elements, 7 unique values. So naively, if you were to just like write a decision tree algorithm from scratch, there would be 6 splits to explore here, right? You'd have to choose, consider the split feature less than 2, feature less than 3, sorry, feature less than 5, less than 9, less than 11, et cetera, et cetera, et cetera, right? Each of those splits, it takes time, it takes effort, it takes memory to compute the gain of that split. So what LightGBM does is one time before training begins, it buckets features into histograms. So it'll roughly divide them into equal quantiles. And there's like some magic in how that happens. It's not exactly quantiles. But basically like small values will be grouped together, large values will be grouped together. And then when LightGBM evaluates splits, it only has to compare the boundaries between those histograms instead of all of the boundaries between all of the unique values. And so that means there are many fewer splits to consider. And the LightGBM papers describe how this greatly improves the training speed with not too much impact on the statistical performance. And in fact, like you can even think of this as a slight form of regularization because you're giving the model like a little bit coarser view of the data. And I should add that XGBoost now supports this feature as well. They have for a little while. It is not the default in XGBoost, but you can do something similar with the XGBoost tree learner called GPU Hist. So XGBoost has also added support for this. Let me take another sip of water. Okay, the next feature I want to talk about that makes LightGBM fast is something called exclusive feature bundling. So this is a way that LightGBM fast. This is the way that LightGBM deals with sparse features. And so in this very simple example from this blog post I really like, we've shown two features, and you can see that they're sparse, right? By sparse, I mean when one is non-zero, the other one is always zero, and vice versa. This might come out of something like a one-hot encoding scheme, but this can show up in continuous data too. This doesn't just have to be coming from categorical data. Okay, like, for example, I've worked with data sets before from refrigerated trucks, and you might have something that's like the amount of power consumption currently going to the refrigeration unit and the engine speed. And if the refrigeration unit is off, you can have a period where that thing is zero, and maybe that's always zero when I don't know, when some other continuous measure, like maybe when the engine speed is in a certain range or something like that. Anyway, what LightGBM will do is it'll handle this transparently through something called feature bundling. So LightGBM has an algorithm built into it to try to combine these features into a single feature. This is another step to reduce the number of split points that have to be explored. And that is like really the main way that LightGBM speeds up work is by just reducing the number of these split points that have to be checked. So you can see here that kind of what happened is in this new kind of composite feature that LightGBM creates, the values of feature one in those last four rows, those were exactly preserved. And then the values of feature two had the maximum of feature one added to them. And so in this way, this looks like an ordinal variable, right? It looks like there's some, or continuous variable, I guess. It looks like there's some scale here. But what you've really done is you've made sure that all of the values of feature two end up in a different numeric space than all the values of feature one. And so this will give you a similar behavior to using one-hot encoded features, but there are a lot less split points to consider. And you can end up with a split point that isn't as rigid as one hot, right? So if you ended up with a split that's like less than 4, that would mean the high end of feature 1 plus all of feature 2 end up on one side of the split, and then the lower part of feature 1 end up on the other side of the split. Don't worry if you didn't follow that, but that's just a little bit of the secret sauce of LightGBM. Okay, and then LightGBM has a built-in framework for distributed training, which I've described before. I won't go too deep into the details of this, but basically this framework uses one of the MPI collective operations called reduce scatter. The way to look at this may be a little bit confusing, is that in LightGBM distributed training, at least in the mode that I'm going to talk about called data parallel, each worker process only has a piece of the overall training data. And then while they work through the process of adding new nodes to the global model, each worker is responsible for evaluating splits on only the piece of data that it has, and then communicating the results from only that piece of data back to the other workers. And so this is different from other parallel frameworks where every worker has all of the data, but then they each work on a subset of it and do some like global stuff. So the thing to take away from this is each LightGBM worker only has a subset of the overall training data. Okay, with that is the end of the kind of lecture part of this. You can read a lot more in the LightGBM paper if you want to go deeper into LightGBM. But with that, let's move to the demo. Aaron, are there any questions before I go to the demo?
No questions. Go for it.
All right. Thank you so much. Let's do it. So let me get my stuff here. Okay, so the demo that I'm going to walk through for you today is available on Saturn Hosted. You can go to saturncloud.io and try this out for free. If you already have a Saturn community login, then that's great. You can come to this projects page and click the big LightGBM button. When you do that, that's going to create a new Saturn project for you called LightGBM. So I've already done this ahead of time, but I promise there's no trickery here. If you click the button, you're going to get the exact same code and project that I have. And let's take a look at that. So when I say project in Saturn, this is kind of like a workspace. We guarantee that all of the dependencies are the same in that workspace because every resource you create in this project has the same container image. In this case, this is an image that we've built on Saturn community specifically for working with this LightGBM example. We also, have like a little bit of random code that's going to run at the beginning of this. You really don't need to worry about what that code does. But what I want to stress to you is that because we're in this thing called the Saturn project, that little code is going to run on the startup of every Dask cluster, every Dask scheduler, every Jupyter notebook, every deployment, everything that I do. So everything is kind of nicely bundled together here. And then before this workshop started, I already started up a Jupyter server and a Dask cluster. And I did that here in the UI, but you can also do that programmatically, as I'll show you in a minute. Okay, let's jump into some code, and then we're going to come back to Saturn later. So from here in Saturn, I can see that my Jupyter is running, and I'm going to click the Jupyter Lab button to open up the Jupyter Lab instance running in here. And for this project, because I created it by clicking that big LightGBM button, we've already seeded this specific project with a nice little README explaining the LightGBM example and a notebook that you can run. So this is all going to be available completely inside Saturn, but you can also access this notebook on GitHub. This is publicly available, released under a permissive license. You can do that as well, but I think you'll have a better experience just clicking the big LightGBM button in Saturn. Okay,
can you actually zoom in a couple
yeah, of course.
On this one? Yeah,
of course. Let's see if I can.
Okay, perfect. It's great.
Oh, there we go. How's that? Good.
Looks good.
All right. Okay, great. So in this example that I'm going to walk through with you, we're going to use a public data set called the New York City Taxi data set. You have probably seen this data set in a lot of conference presentations and documentation. People really like using this data set for machine learning examples because it is publicly available. It's large and diverse enough to be interesting. And it's tabular data with a decent number of features. So you can explore and do a lot of interesting things. So in this data, every observation is one taxi trip in New York City. And what we're going to do is we're going to use LightGBM and Dask to build a LightGBM regressor to try to answer the question, based on the things that I know at the beginning of a taxi trip, can I predict what tip this trip is going to earn as a percentage of the total fare? So we want to see are there certain locations or times of day or something like that where people are tipping more? Okay, so remember that I said before that you can set up a Dask cluster programmatically in Saturn if you want. Now, I've already done this before the workshop started, and I want to show you a little bit about that. If I went back to the Saturn UI, I'm in my LightGBM project. You can see I have this Dask cluster attached to my Jupyter. If I click running, this is going to take us to the Saturn logs view, where you can see that I have a scheduler, this other thing called a queue cluster, and 3 workers. So this is a 3-worker Dask cluster. If I come back here, you should have also seen this link called dashboard. I can actually pull up, I'm going to put the zoom thing down there. Okay. I can actually pull up the Dask diagnostic dashboard. So this is running inside of Saturn. I'm only able to access this. I'm the only one able to access this because I'm logged in to my account, but I can just view this in my browser and see what's happening. So at this point, I'm not doing anything, so this doesn't look very interesting, but you can see I have my 3 workers. Each of them, they have about 14 gigs of available memory, and they're each running with 2 threads. And that's because of the settings that I chose here. I chose for each of them to have 2 cores and 16 gigs of memory. You could choose much larger instance sizes if you want. But for this demo, I wanted to go cheap and fast. Okay, so if I had wanted to create that cluster programmatically, I could use this library called Dask Saturn. Dask Saturn is an open source project that we maintain at LightGBM, at Saturn. It is a client for Dask clusters in Saturn. And you can use this method to describe sizes to see the different options that you have for the size of the worker and the scheduler. And I hope you'll notice you also can use fairly large instances with GPUs as well. Remember when I was talking about the client and the scheduler and the workers, I talked about how there's this clean separation between, the client and the rest of your code. This cell right here is the only place where your code is going to need to know that it happens to be on Saturn. I'm going to connect to a Saturn cluster, create a client, and from this point forward, LightGBM is going to be like, okay, it's some Dask client. I don't really care that it's Saturn. I'm going to do LightGBM Dask stuff. When you use this Dask Saturn client, and I run this little bit of code, notice that this returned immediately, right? What's happening here is because you're inside Saturn, this client can take advantage of that, and it knows that there's already a cluster that looks like the one that I described available and attached to this Jupyter. So instead of creating something new, it's just going to attach to that and be like, here's a client. What that means is you don't have to write a bunch of code to be really, really careful that you don't accidentally create multiple clusters that you have to remember to shut down. It's one of the nice things about the Saturn client. So now we have our client, and we're ready to rock. You can pull up this little widget here in Jupyter by printing the cluster, and this will tell you, I did something wrong. It's probably my browser cache. I apologize for that. This should tell you a little bit about the number of workers. But again, as I showed you earlier, you have this Dask diagnostic dashboard. I promise I'm not lying to you. Here are the 3 workers. Here's the memory that they have. And I'm going to show you them doing some stuff in a second. All right, so we have our Dask cluster set up. Let's start doing some work. The first thing that we're going to do is read in some training data. So all of the New York City taxi data, that data is available for free from this publicly readable S3 bucket. I'm going to read in 1 month of data from 2019. I'm going to do this with the Dask DataFrame module. So remember from the talk, the Dask DataFrame, it looks and feels like pandas, but it's actually a distributed data frame that basically breaks all of your data into multiple smaller pandas data frames. So let's run this, and then it's going to be quick. I'm going to go try to catch the tasks running in the dashboard. It was really quick. I didn't get it. I'm sorry. But what you should see now is that the workers have a little bit more stuff in memory. And partially what's happening here is that I'm sampling some of the data. So let's actually just give it a bigger chunk. So here we had 130 megs. Let's just do that again. Oh, right. I haven't actually asked for this data yet. I apologize. Since I've done this so far, Dask has not actually pulled any data from S3 yet. It's just set up this graph of basically some things like those delayed functions that are just saying, hey, when you ask for something, I'm going to do some work. I apologize. So let's ask for something. Let's ask Dask to compute the total size of this data set in memory. And now once we do that, now there's some stuff going on, right? Now there's all these tasks running and there's all this stuff. You can see in this view kind of the tasks that are running, the amount of data that's been stored. We can look at the graph view to see the task graph. You can hover over these to see what's going on. And now we're done. And now if we look at the worker memory, remember before we were in the range of 150 megs in memory. Now each worker has close to 500 megs in memory. Okay. Very similar to pandas, you can use some of the operations you know and love from pandas to explore this data. So we can print a couple rows with head. We can use dtypes to see the schema. And there you go. We have our data set. We're ready to go. And remember, this data set's total size was just short of 4 million records and just short of a gigabyte. Okay, So next we're going to do feature engineering in Dask. We've written this function that does stuff you're probably used to from pandas. This function is just, it's adding columns, it's using pandas e methods like, isocalendar.week, stuff like that. And notice that this all works by reference. We're just going to pass a Dask data frame to this function, and it's going to add all these features for us out in parallel. Okay, let's do that. So notice how quickly this call returned. That's because, again, at this point, the work that I've done is lazy. It's just saying like, hey, when I ask for this result, Dask, please go do this stuff. Let's do that right now. So what I'm going to do is I'm going to use a method called persist. So before, when we were looking at some characteristics of the data, Dask was like doing that work, it was computing things, and then it was getting rid of those results once it was done. It said like, we don't need this anymore. With persist, I'm saying execute all of this stuff. I'm using the function wait to say, don't run any other code until this stuff is done executing. And then persist says, keep that stuff permanently in memory on the Dask workers. So if you run this and go look at the work that's being done, now you can see that there's more CSV reading happening again. And our feature engineering is happening. We're filling in NAs, and I think we may be done. And we're done. So now that data set is sitting there in memory. You can see the memory utilization went up on the workers a little bit more. And now like that data set, if we want to keep using it for machine learning experiments, we don't have to reread it from S3 every time. Okay, and let's just check the size again. Beautiful. So the data set has gotten smaller because that function that I showed is not only doing feature engineering, it's also doing feature selection and dropping a bunch of unnecessary columns. Okay, so we have our data. It's in this distributed collection. I forgot to show you. We can look at just how distributed it is with this method nPartitions. So you can see we have 11 different blocks. So this one data frame is made up of 11 smaller data frames. So now we have our data. It's in a Dask data frame. If we look, I'll show you one more thing. If you look at the memory utilization here on the client, so this is running on the Jupyter, I'm only using 1.3 gigs of memory. And my CPUs are barely doing anything. So this is just like another small piece of proof that this work is happening in the Dask cluster. The data is out there. It's not here in this Jupyter. Okay, so we have our data set up. We're ready to go. Next, let's train a LightGBM model. Don't worry about this shell code if it doesn't make sense, but I left a note here to be sure that I explain one more time that the features that I'm going to show you right now, they exist on LightGBM's stable branch, but they have not been released to a package manager. So if you pip install LightGBM or conda install LightGBM after this talk, you are not going to be able to run any of the Dask stuff. This is another advantage of the Saturn project setup. So everything that runs in the Saturn project will run in a Docker image that we've already created that already has LightGBM installed from source. So you don't need to run this code yourself or figure out how to run this code every time you set up a Dask worker. Okay, so let's import LightGBM. There we go. And next, let's set up our data. So right now, this taxi train data set has both our features and our target. Remember that our target is the total tip, the tip as a percentage of the total fare. Okay, that returned really quickly because again, this subsetting operation is another one of those cases where I'm creating like a task graph for Dask to run, but Dask hasn't actually done anything yet. And finally, let's train a model. So hopefully, if you've used the scikit-learn interface to LightGBM before, this should look very similar. And that's our goal. I mentioned before that in other parts of the Dask ecosystem, there is this overarching goal of making the code look and feel just like the non-Dask equivalent. We wanted to do that in LightGBM as well. And XGBoost has the same aim. So you set up your Dask LightGBM regressor with exactly the same types of parameters that you would set up for a non-Dask one. And then the only difference here is that at this point, you pass a Dask client into the fit method. So let's do this and go watch what happens. Okay, so you can see all these other tasks are done, and we have these 3 tasks called train part. what's happening here is that we don't have a LightGBM native implementation in Dask, which means what's happening is we have these 3 long-running LightGBM tasks, 1 per each worker in the cluster, that are then wrapping LightGBM C++ code that's doing all the LightGBM distributed stuff. So it's not like we've rewritten the LightGBM algorithm from scratch all the way down to like the matrix manipulations using Dask primitives. That's not what we've done. What we've done, what XGBoost has done, is just basically use Dask as a wrapper to control our built-in kind of distributed training thing. But here we go. Training is done. Took about 30 seconds for 4 million row, I think 10 column data set with 258 iterations and max depth 5. So like, I don't know, I feel like that's not bad. And I want to show you some features of this model object, and then we can see how well the model did. So the first is that this model object is an instance of this Dask class, but that doesn't mean that because you trained your model using Dask, now when you go deploy it, you have to have Dask in your scoring environment as a dependency. You absolutely do not have to do that. And you have a couple options here. So you can use this method toLocal, which will pull out of the Dask model object the LightGBM scikit-learn equivalent. And that thing can be loaded and used without having any Dask dependencies installed, which is cool. You also can go even further, reach all the way into this object and grab the LightGBM booster. So LightGBM booster object is like the core LightGBM model object. And you can use that as well. And you can do like interesting stuff with this. Like for example, you can get a data frame representation of the entire model if you want. So you can see like the split point and feature that was chosen for every node if you like really, really want to get deep into your model. Okay, anyway. And then you have a couple of options for deploying these models. So you can directly pickle a Dask LightGBM regressor if you want. It just means that when you unpickle it, you'll have to have Dask dependencies available, you know, Dask and distributed Dask ML. You can grab the scikit-learn interface like I showed. You can save the booster. You can do any of these things. And then, you know, push that model object to S3 or you know, your deployment thing of choice. Okay, the last thing that I want to show before we move to Q&A is let's see how well the model did. And I'm going to show how we can use the prediction interface in Dask LightGBM, or excuse me, LightGBM.Dask to do this. So let's load another month of data. I trained on January 2019. So let's test on February 2019. Notice again, this code ran extremely quick, and that's just because nothing has really happened yet. We just set up a Dask graph. I am going to run our same feature engineering code and then ask for the result of that. So if we go back to Dask, I might not have been fast enough. There's work going on, CSVs are being read, and our results are already there. And then I can directly use the predict method on the Dask LightGBM regressor, just like you would in the normal non-Dask interface to get some predictions. That returns immediately because that method will return a Dask array. And so that's lazily evaluated. That won't run until you ask for it. And in this case, to see how well we did, I'm going to use some of the built-in metrics from Dask ML. So Dask ML has these metrics functions that have identical APIs to the scikit-learn metrics functions, but instead of expecting local data, they can take in Dask data frames and Dask arrays. And let's see how well we did. I'll just tell you that's honestly like not fantastic. I didn't really spend any time, you know, trying a lot too many features or tuning hyperparameters. So this target variable is distributed between 0 and like, I think 0.3 or something like that. And so a mean absolute error of 0.14 is like pretty bad. It's like kind of like a mean absolute percent error around 50%. But the purpose of this was not to show you that like I produced a great model with no effort. You know, what Dask brought us here was the ability to bring more hardware to bear on the problem to iterate faster. Dask is not going to magically make hyperparameter tuning go away, you know, or feature engineering. Okay, Is there anything else that I want to talk about with this? I think that that's the extent of the demo that I wanted to show. Hopefully you've seen that it's not too difficult to get started with LightGBM and Dask. And then I guess I just have one more thing that I want to talk about, and we can open it up for questions and answers. Okay, so if you'd like to go try this example yourself, you can go to Saturn Cloud Community. Just log in if you have an account already. If you don't, you can create a free account. Running these examples is not going to cost you money. And if you go to that projects page that I was on, it's kind of the place you're going to land when you log in. Click the big LightGBM button. This notebook will be there, and you can run it exactly. You can try changing the parameters, using your own data, and kind of do whatever you want. With that, I'd like to open it up for questions, and I'll leave this slide up. If you want to explore more beyond just LightGBM, you can go to our website to see kind of what other events we have coming up. You can go to the Saturn Cloud events page. We do have a Slack community where you can ask for support, ask questions, talk to other people who are using Dask and Saturn and some of these other tools together. And yeah, thank you so much for your time and attention. With that, I'd be happy to answer any questions.
Awesome. Well, thanks, James. That was a great talk. We do have one question right now in the chat. It's asking about GPU support. So there's this latest version of LightGBM support GPUs with Dask, if that's available.
Great question. So you should not expect that the new release of LightGBM will support using Dask and the GPU version of LightGBM. But let me give you a couple caveats to that. So first, I'm going to show you a GitHub issue that you should go subscribe to so that you can be updated when that happens. Let me say a couple things. You should definitely not expect that in the next LightGBM release, you'll be able to use something like a Dask cuDF data frame where LightGBM's Dask interface uses, where LightGBM's Dask interface takes advantage of the fact that your data is already distributed in GPU memory on different GPUs using Dask cuDF. That's not going to happen. Like, that will not be supported in the next release. I recommend that you subscribe to this feature to keep up to date on the developments there. I don't know, I'll just be honest with you, whether or not the Dask LightGBM interface that uses the OpenCL-based LightGBM GPU package, I don't know how well and whether that works. It's not a thing that we're testing. Since we merged the code from Dask LightGBM into LightGBM about a month and a half ago, about 2 months ago, we've been focusing on kind of the main CPU cases, making sure that the interface looks right, making sure the documentation is usable. So I just genuinely don't know. We haven't tested that. It's possible that you can do a GPU-based build of LightGBM, not the CUDA-based build, but the OpenCL one, and use that with Dask, with LightGBM Dask, and have it take advantage of the GPU. That will involve moving data between main memory and GPU memory. And I can tell you, you'd be out on a path that is like untested and hardly documented. So I know that's kind of a roundabout answer. The answer is, if it's for something that needs to be reliable and definitely needs to work, don't try to do it. But it might work. It hasn't been the highest priority yet. What else can I answer?
Awesome. Any other questions? We have a few more minutes. I also dropped in the link to our Slack community here. They're available on the slides there too. But if you want to click that, you can join there. Some other question comes up to you later. Both James is on there, I'm on there, and a few other people, and a lot of people in this community are also there in case you have any more questions or want to try things or try Saturn. I'll give just a few more seconds for any last questions to roll in. Otherwise, we'll go ahead and wrap everything up. Going once, going twice. Okay. Oh, wait. Somebody said wait. I didn't give enough time to type. All right.
Okay.
Charles, we'll wait for your question. Don't worry. You don't need to rush. We'll be here.
We're in no rush. While we wait for that, I can show. If you are interested in contributing on the LightGBM Dask integration, because this code is so new and it's a fairly large addition, there are a lot of rough edges. There are a lot of things to be fixed. You can actually come and look for the Dask tag in LightGBM's issues and look for any of these things. The way that we manage feature requests in LightGBM is a little different than other open source projects. You can also click on this feature request pinned issue. And if you search for Dask here, you'll see there's a whole bunch of Dask feature requests. So the way that we manage this in LightGBM, these issues on the issues page are closed. And then we use this one kind of large issue to track the set of ones that are still open. So if any of these things look interesting to you, you can leave a comment on the corresponding issue and say that you'd like to pick it up, and we can advise you on whether it's something that an outside contributor can do. But we would welcome people trying it, people using it, people opening issues, contributing. Always welcome to that.
There was one quick question asking if the recording's posted. Yes, it will be. If you want to watch if you go to saturncloud.io, our events page has all the upcoming and past events, so you can find the links there. But you can also find it on our YouTube channel. We'll get that posted within the next couple of days, so you can stay tuned for that.
I also should say, I forgot to mention, we have a very detailed tutorial in the Saturn documentation on how to use LightGBM with Dask. So at this moment, this tutorial still uses Dask LightGBM, not the native LightGBM. And that's because we didn't want to have this documentation relying on a package that isn't on a package manager yet. But many of the concepts in here are the same between Dask LightGBM and native LightGBM. So for example, there is a large section, what might be most interesting to this audience. There is a large section on all of the different ways, all the different parameters that you can tune and play with, both on the Dask cluster setting and in LightGBM's own training, to make your training faster or to improve the accuracy, things like that. So you might want to consider some of those tips if you go deeper into Dask and LightGBM.
Awesome. So we had another question, which was about LightGBM and XGBoost, like integrations, and mostly related to Dask versions and Python versions. There's a question because someone's had issues with like Python 3.8, 3.9, and then it looks like an older version of Dask. Do you have any opinions or guidance on different versions?
I can speak a little bit to that. So I don't know how long ago, a couple, at most 3 months ago, I don't remember how long ago, LightGBM officially dropped support for Python 2. And right now, the oldest version of Python that LightGBM supports across not just Dask, but all LightGBM is version 3.6. For the Dask module, we test it on Python 3.6, 3.7, and 3.8. We have not done any 3.9 tests. So if whoever asked that question would like to try to build LightGBM from source using, or play around and would like to try it on 3.9 and report to us any bugs, I would welcome that. I don't know. I just don't know. We haven't tried it yet. If the Dask, if any part of LightGBM will work easily on Python 3.9. We haven't tried that yet. For XGBoost, I don't know. I'm not sure about that.
Yeah, and for who asked the question, if you want to kind of join the Slack community, we can definitely take that conversation further, because it sounds like there's a mix of a couple different packages and versions that you're having trouble with. So we definitely love to, we can open that up to the community for other people who have opinions on it too.
That's a great point. I would love to talk about that in Slack. I would be happy to share my, so I am the developer that's kind of spending the most time on the LightGBM Dask integration now. And so I end up testing a lot of weird different versions of LightGBM from source with Dask. And I have a little repo that lets you do that in Docker and like do it fairly easily. So if we talk in Slack, I'd be happy to share that. And it might be a way for people who want to explore to try to do that.
Cool. Okay, we have a couple more questions. Someone's asking about saving to Onyx, ONNX format. Is that something that LightGBM does, or any sort of other serialization?
There is a project that is not, so let me back up. So LightGBM is a Microsoft project, and you know that Microsoft loves Onyx. So there is a project. So the short answer is yes. There is this project called Onyx ML Tools. This is not maintained by the LightGBM maintainers. That does have a LightGBM converter right here. So Onyx/Onyx ML Tools. I have never used it. I cannot speak to whether or not it plays nicely with newer versions of LightGBM. It's not a thing that we maintain, but it does exist. There's another project that you can use with LightGBM as well. If you're looking for like more serialization formats that are kind of framework agnostic, there is another project called Treelight that can also be used for LightGBM models. I don't remember where their LightGBM docs are, sorry, but I believe that project will also support LightGBM models. And I'd say in general, if you're interested in these other extensions, if you look in the LightGBM README, we try to keep a running list of all of these other extensions that do LightGBM stuff. And if you know of others, we would welcome contributions to add them. So yeah, see, here's Treelight. You can convert LightGBM to PMML. I don't believe that there's a LightGBM converter for PFA, but you might be able to do it in 2 steps. You might be able to go like LightGBM, PMML, PMML to PFA if you're using PFA or something like that. So there are a lot of options. Hopefully that answers the question.
Yeah, and so the question was asking, there's one other clarification specifically about scoring in the JVM. So probably the PMML might be a good route to go for that.
Yeah, so if you're doing JVM stuff, PMML is a good project. PFA has great support in the JVM through a project called Hadrian. Hadrian is like basically a project that lets you code generate Java code from a PFA. There is also a project called MML Spark from Azure. And don't let the name deceive you. This is also a generic LightGBM on the JVM project, if you'd like. And I can tell you even more about this. So MML Spark is a cool project that might be useful for you. LightGBM from this main repo does produce a jar that allows you to use LightGBM's low-level API from Java. So let me go to an actual release. If you go to the release, you're going to see these 3 jars: LightGBM lib, Linux, Mac, and Windows jar. So what we do in LightGBM is the main logical library is implemented in C++ with a C interface, and we use a project called Swig, S-W-I-G, to basically generate a Java interface to that code. So you might be able to, for example, train a model in Python, extract the booster object, save that booster object with its built-in save method, and then load that booster into the JVM using the lib-LightGBM jar. I've never done that. I'm not a Java or Scala or Kotlin developer, but in theory, those things should all work together. And if you tried and they don't work, we would greatly appreciate an issue describing what you tried to do. But I just did want to make that point that when I talked in the notebook about saving the booster, right here, the booster save method is a language agnostic save method. It saves a huge text file that describes the fitted model. And so that text file can be read by all of those other wrappers. I'm sure that was way more information than you needed, but hopefully that convinces you. LightGBM on the JVM is totally a thing.
Looks like we've got time and we've got one final question. Somebody's asking if this LightGBM Dask module integration is faster than using like native LightGBM and then doing it with Dask features, I guess, a little bit more manually.
Okay, yeah, great question. So I would not expect that Dask LightGBM, that I'm going to start saying LightGBM.Dask. Dask LightGBM is like the old product. I would not expect that LightGBM.Dask on multiple machines would be faster than using LightGBM on a single machine that has the same cumulative resources. There's overhead introduced by the Dask framework, right? There's data that's moved around. There's communication overhead. So you shouldn't expect that to be faster. But at a certain size of problem, getting and keeping that larger machine is not feasible, either because of availability, because of maybe your budget or whatever. So Dask won't, using Dask with LightGBM, I wouldn't expect it to be faster than using the same total cumulative resources on one machine, but it should make it more possible to use that many resources, because it's usually easier to get several small machines than it is to get one machine. There's a couple other things that you should think about though too. When we talk about faster or slower, it's not just the comparison. It wouldn't be fair to only compare training times once the data is already prepped, right? So Dask can take advantage of, loading data in parallel. That might not be possible on a larger machine, maybe. Dask has some nice caching mechanisms in it for reusing data sets that you might not get if you were just going like pandas to scikit-learn transformers to LightGBM interface. So there are some other kind of side benefits to using Dask. I think that the largest one is that it allows you to burst up quickly to the size you need, do the work, and then burst back down a lot more easily than you could by, say, like provisioning a new virtual machine and then deprovisioning it. I hope that answers the question. Now, the next question was, well, couldn't I just do this myself with delayed functions? That's how I interpret the question. The answer is yes, you could. I don't encourage it. It is more complicated than you might think to get it right. So doing that successfully, will require you to understand LightGBM's kind of built-in distributed computing framework written in C++. So you'll have to understand that. You'll have to understand the order that things are called and how the different machines talk to each other. And then you will also have to implement a lot of the stuff that we take care of for you in the way that data is chunked. So I'll give you an example. I created this Dask data frame with 11 partitions, right? It's 11 pandas data frames spread across 3 physical workers. It would be inefficient for us to run 11 LightGBM worker processes on those 11 chunks, given that we only had 3 physical machines and 6 CPU cores, right? Because with only 6 cumulative CPU cores across the 3 machines, if we had 11 worker processes, they'd all be competing with each other. So one of the tricks that we do inside LightGBM.Dask is we smush together, that's an official term, we smush together all of the partitions that are physically on the same worker. So there's no moving data around the network. And we only have one LightGBM worker process per smushed ball of data. And so that means like LightGBM is just automatically taking the best possible advantage of the physical resources available to Dask. If you tried to roll your own thing in delayed, you would have to figure that out yourself. Hopefully that answers the question.
Yes, I think so. Well, great questions, everybody, and great answers, James. Thanks for all of the info that you've provided. We're just a couple minutes over time, so we're going to have to end the session now. Again, find us on Slack. You can check out the recording of this later in just a couple days off of our website. But thank you again, James, and have a good one, everybody.
All right. Thank you, everyone.